Imagine looking up at the night sky and realizing that every twinkling star is an unreachable island, locked away by the unbreakable laws of physics. The universe is a vast, beautiful cage, and humanity is trapped on a single speck of dust. But what if the laws we thought were written in stone could actually be bent? What if the ultimate cosmic speed limit isn't a wall, but a doorway? For generations, travelling faster than light was dismissed as pure science fiction, a fantasy reserved for Hollywood movies and dreamers. But right now, in quiet physics laboratories across the globe, a profound transformation is happening. The impossible is becoming theoretical, and the theoretical is creeping closer to reality. This is not just a story about rockets or engines. It is the ultimate chronicle of how humanity might finally break its cosmic chains and conquer the stars. Let us begin by confronting the true scale of our isolation. When you look at a typical map of the solar system, it fits neatly onto a textbook page. Earth sits comfortably next to Mars, and Jupiter appears just a short skip away. But these maps are complete lies designed for convenience rather than accuracy. The reality of space is defined by its name. It is mostly just empty, unfathomable space. If we were to scale the Earth down to the size of a tiny glass marble, the Moon would be a small pebble located about 30 centimetres away. To reach Mars on this exact same scale, you would have to walk more than 70 metres down the street. Jupiter would be blocks away, and Pluto would sit on the completely opposite side of a massive city. And that is just our immediate celestial neighbourhood, a tiny backyard in a sprawling universe. The moment we look beyond our Sun toward the nearest star system, Alpha Centauri, the scale explodes completely out of comprehension. On our marble Earth scale, Alpha Centauri would not be in the next city, or even the next state. It would be located thousands of kilometres away, across an entire ocean. To cross that terrifying void using the fastest technology humanity has ever constructed would take an agonisingly long time. The Voyager 1 spacecraft, travelling at a blistering speed of over 60,000 kilometres per hour, would still require more than 70,000 years to reach our nearest stellar neighbours. If ancient humans had launched a rocket during the last ice age, it would still be drifting through the empty darkness today, nowhere near its destination. This brings us to the fundamental barrier of modern space exploration, the tyranny of the rocket equation. Invented by Konstantin Tsiolkovsky at the turn of the 20th century, this mathematical law acts as a heavy anchor dragging down our ambitions. It dictates a brutal reality. To move mass through space, you need fuel, but fuel itself has mass. Therefore, to push that fuel, you need even more fuel, which adds even more weight, requiring an even larger fuel tank. This creates a vicious, exponential cycle of compounding weight. To accelerate a standard human-carrying starship to just a fraction of the speed of light using conventional chemical propellants, you would need a rocket larger than the entire observable universe just to hold the necessary fuel. Even our most advanced concepts, like nuclear fusion rockets or massive antimatter engines, run face first into this unyielding mathematical wall. They are simply too heavy, too inefficient, and too limited to ever bridge the gap between worlds in a human lifetime. Faced with this mathematical dead end, scientists realised they needed a complete paradigm shift. If we cannot push a ship through space fast enough, perhaps we can change the way we think about space itself. This radical line of thinking led directly to the doorstep of Albert Einstein and his revolutionary theory of general relativity. Einstein fundamentally altered our understanding of reality by showing that space and time are not an empty, rigid stage upon which cosmic events unfold. Instead, they form a smooth, flexible fabric known as spacetime. This fabric is dynamic, it can be stretched, is compressed, twisted, and warped by the presence of mass and energy. A heavy object, like a star or a planet, acts like a bowling ball dropped onto a soft trampoline, creating a deep depression that pulls other objects toward it. This warping of the cosmic fabric is what we perceive as the force of gravity. It was this profound insight that opened the door to a radical loophole in the cosmic speed limit. Einstein's theories clearly state that nothing can travel through space faster than the speed of light. Light moves at roughly 300,000 kilometers per second, and accelerating any physical object with mass to that speed would require an infinite amount of energy, which is a physical impossibility. However, Einstein's equations contain a magnificent hidden twist. While nothing can travel through space faster than light, space itself has absolutely no speed limit. Space-time can expand, contract, or distort at any speed it desires, even at speeds that vastly exceed the velocity of light. We know this is true because it has already happened. During the earliest moments of the Big Bang, a period known as cosmic inflation, the fabric of the universe expanded at a rate far faster than light, carrying newborn galaxies away from one another at mind-boggling velocities. For decades, this loophole remained a fascinating but unexploited quirk of physics, until a young theoretical physicist from Mexico named Miguel Alcubierre had a moment of profound inspiration while watching an episode of Star Trek in 1994. Alcubierre wondered if the warp drive depicted in sci-fi could exist within the strict framework of real mathematical physics. He sat down and worked backward from Einstein's field equations, instead of starting with a known source of matter and seeing how it curved space. He designed a specific desirable shape of warped spacetime and calculated exactly what kind of matter would be required to create it. The result of his calculations shook the scientific community to its core and became known as the Alcubierre metric. The concept Alcubierre proposed was elegant yet utterly mind-bending. Instead of a rocket blasting through space using fiery propulsion, a starship equipped with a warp drive would remain completely stationary inside a localized pocket of normal space-time, which he called a warp bubble. The magic happens entirely at the boundaries of this bubble. The warp engine would violently compress the fabric of space directly in front of the spacecraft, while simultaneously expanding the fabric of space directly behind it. This would create a steep cosmic hill. The space ahead would contract, pulling the destination closer, while the space behind would stretch, pushing the starting point further away. The ship inside the bubble would effectively surf on a wave of distorting space-time, moving across the universe like a passenger on a cosmic moving walkway. Because the ship remains completely at rest relative to the space immediately surrounding it, it experiences absolutely no acceleration, no crushing g-forces, and no violation of Einstein's local speed limit, even if it crosses vast interstellar distances in a matter of hours. When Alcubierre published his paper, it was hailed as a brilliant mathematical triumph, but it quickly ran into a catastrophic practical problem. When scientists analysed the math required to create this warping effect, they discovered that compressing space required normal gravity, which is easy enough to understand, but expanding space required something completely unprecedented: anti-gravity. To stretch the fabric of space behind the ship, the warp drive would need a ring of material with a negative energy density, a concept commonly referred to as exotic matter. Exotic matter is not just regular matter with an opposite electrical charge, like antimatter. It is a theoretical substance that possesses less than zero mass. If you held a brick of exotic matter in your hand, it would weigh less than nothing. And if you dropped it, it would fall upward, repelling away from the Earth rather than being pulled down. The requirement for exotic matter immediately cast a long, dark shadow over the dream of warp travel. While negative energy states can exist in minuscule amounts at the subatomic level through quantum phenomena like the Casimir effect, scaling this up to a macro level seemed completely impossible. Worse still, early calculations indicated that the amount of negative energy required to fuel a single Alcubierre warp drive was absolutely staggering. To transport a modest-sized spacecraft across the stars, you would need an amount of exotic matter equivalent to the entire mass of the observable universe. Later refinements by other physicists managed to reduce this requirement significantly, bringing the necessary mass down to roughly the size of the planet Jupiter, and eventually to about the mass of a modern SUV. Yet even a few grams of a substance that might not even exist in our universe is an insurmountable barrier to engineering. For 30 years, the Alcubierre warp drive remained a beautiful mathematical curiosity, a tantalizing proof that physics allowed for faster-than-light concepts, but one that was entirely dead in the water because it relied on magic ingredients. The scientific community largely moved on, viewing warp drives as an impossible engineering dream, until a massive breakthrough occurred that completely shifted the paradigm. A new wave of physicists decided to look at the problem from an entirely different angle. They asked a fundamental question: is it possible to create a warp bubble using only regular positive energy matter, the kind of normal stuff that makes up stars, planets, and human beings? For a long time, the consensus was a resounding no, backed by various mathematical theorems that seemed to forbid positive energy warp drives. But in the early 2020s, advanced computational tools and fresh perspectives began to chip away at these long-held assumptions. The true turning point arrived when researchers began exploring the physics of solitons. A soliton is a self-reinforcing isolated wave that maintains its shape and velocity as it travels through a medium without dissipating or breaking apart. You can observe solitons in everyday life, such as a solitary wave rolling down a canal or a stable smoke ring drifting through the air. Physicists realized that a warp bubble is essentially a soliton made of pure spacetime. If they could find a configuration of normal matter that could form a stable spacetime soliton, they could bypass the need for exotic matter entirely. This line of research culminated in groundbreaking papers that sent shockwaves through astrophysics journals. Teams of international scientists working independently discovered mathematical solutions to Einstein's equations that described physical warp drives powered entirely by positive energy. By altering the shape, thickness, and geometry of the warp bubble's wall, they proved that you do not need anti-gravity to modify spacetime in a meaningful way. Instead, you can use ultra-dense shells of ordinary matter arranged in complex, precise configurations to create the necessary gravitational distortions. This discovery completely shattered the 30-year-old dogma that warp drives required impossible physics. Suddenly, the conversation shifted dramatically from the realm of science fiction and theoretical philosophy into the practical domain of extreme structural engineering and numerical relativity. To fully grasp how these modern positive energy warp drives function, we must look closely at their unique geometry. Unlike the classic Alcubierre model, which relies on a ring of negative energy to violently stretch space, these new models utilize a multi-layered shell of extremely high-density matter. This shell is engineered to possess an immense gravitational field that is meticulously sculpted. By precisely manipulating the internal stresses, pressures, and rotational speeds of the matter within this shell, engineers can create a highly localized gravitational gradient. This gradient acts as a powerful lens, bending and warping the surrounding space-time fabric into a bubble shape. Inside this bubble, the space remains perfectly flat and calm, ensuring that any crew or delicate scientific instruments aboard the craft are completely shielded from the extreme, violent gravitational forces tearing through the bubble's outer walls. However, resolving the exotic matter problem instantly unveiled a new set of monumental challenges that scientists must now confront. The first and most obvious hurdle is the sheer quantity of mass required to construct one of these positive energy warp shells. While we no longer need imaginary negative matter, the amount of normal matter required is still mind-bogglingly vast. To create a stable warp bubble large enough to house a small exploration vessel, the shell would need to be composed of a material so dense that its total mass would equal that of an entire planet, or at the very least, a massive moon. This mass cannot just be a loose pile of rock. It must be compressed and structured into a highly compact, incredibly thin layer, achieving densities that approach those found in the dead cores of collapsed stars, such as white dwarfs or neutron stars. This requirement introduces a profound engineering paradox. How do you construct a ship that carries the mass of a planet? And how do you manipulate materials at densities where atomic structures completely break down? At these extreme levels, regular chemical bonds cannot hold matter together. The intense gravitational forces would cause ordinary materials to instantly collapse under their own immense weight. Humanity would need to master the art of manufacturing and stabilizing degenerate matter, a state of plasma where electrons are stripped from their nuclei and packed together with extreme tightness. We are talking about engineering at a scale and precision that is light years beyond our current industrial capabilities, requiring us to harvest entire moons and re-engineer their atomic structures from the ground up. Even if we could somehow gather and compress a planet's worth of mass into a sleek, functional starship hull, we are immediately confronted by a terrifying cosmic barrier known as the horizon problem. When a warp bubble accelerates and begins travelling faster than the speed of light, an invisible, absolute boundary forms around it, highly reminiscent of the event horizon of a black hole. This boundary is a direct consequence of relativity. Because the bubble is moving through the cosmos faster than light can travel, signals from the inside of the bubble can never cross the horizon to reach the outside world, and conversely, information from the outside can never penetrate the front of the bubble to reach the interior. This creates a catastrophic operational nightmare for anyone trying to pilot the craft. Once the warp drive is active and travelling at superluminal speeds, the crew inside the central chamber is completely cut off from the rest of the universe. They cannot send a signal to the front of the bubble to control it, adjust its course, or turn the engine off. The ship becomes a runaway cosmic train, completely incapable of steering or braking on its own. For a warp voyage to be successful, the path through space-time must be pre-arranged and laid out before the journey even begins, or the drive must be governed by an automated pre-programmed mechanism that is hard-coded into the structural geometry of the bubble itself, allowing it to naturally decay and collapse after covering a precise distance. Furthermore, the horizon problem introduces an even more immediate danger to the crew inside, Hawking-like quantum radiation. Just as the event horizon of a black hole slowly leaks thermal radiation due to quantum field disruptions at its border, the intense artificial horizon of a rapidly moving warp bubble would generate an overwhelming flood of high-energy particles. This radiation would pour directly into the interior of the bubble, creating a highly toxic, radioactive environment. Without incredibly advanced sci-fi levels of radiation shielding that can deflect or neutralize quantum-level energy shifts, any human crew inside would be instantly vaporized by a relentless torrent of cosmic heat and subatomic particles long before they ever reach their destination. To study these incredibly complex hazardous dynamics without building a dangerous, multi-billion-dollar physical prototype, modern physicists have turned to the digital realm, utilizing advanced supercomputers to simulate the behavior of spacetime. A premier tool in this bleeding-edge field of research is an open-source numerical relativity code known as Warp Factory. Developed by an international collective of physicists and software engineers, Warp Factory allows researchers to input various designs for warp drive shells and simulate exactly how they will interact with the fabric of the universe in real time. Using these sophisticated computational models, scientists can visualize the intense gravitational stress fields, track the flow of energy, and search for unexpected instabilities that could cause a warp bubble to catastrophically rupture. These simulations have provided invaluable insights, revealing that warp bubbles are highly sensitive, volatile structures. If the distribution of mass along the shell drifts out of alignment by even a microscopic fraction, the entire bubble can become highly unstable, warping uncontrollably until it collapses into a violent, localized singularity, essentially creating a miniature black hole that would instantly swallow the ship and everything inside it. But these digital simulations have also revealed a fascinating, unexpected silver lining. Even if a warp drive is incredibly difficult to build, its unique physics mean that it should leave behind an undeniable, highly distinct signature in the cosmos. When a warp bubble accelerates, decelerates, or undergoes a catastrophic structural collapse, it violently shakes the surrounding fabric of spacetime, generating powerful ripples known as gravitational waves. These are not ordinary gravitational waves like the faint, distant murmurs produced by colliding black holes millions of light years away. A collapsing warp drive would produce a sharp, high-frequency blast of gravitational energy with a unique structural footprint that looks completely different from any natural astrophysical event. This realization has fundamentally changed the way SETI, the search for extraterrestrial intelligence, operates. Instead of just listening for faint radio signals or looking for laser flashes from distant stars, astronomers are now realizing that our current generation of gravitational wave detectors, like LIGO and Virgo, along with planned next-generation space-based observatories like LISA, might actually be capable of detecting alien traffic. If an advanced extraterrestrial civilization has already mastered warp drive technology and is actively travelling across our galaxy, the sudden stops, starts, and occasional failures of their starships would send distinct gravitational shockwaves rippling across the Milky Way. We might turn on our detectors one day and discover that the cosmic fabric is buzzing with the unmistakable signatures of interstellar commerce, providing definitive proof that faster-than-light travel is not only possible, but actively in use. Human brains simply did not evolve to accurately comprehend numbers of such immense magnitude. Because of this inherent limitation, we must establish a clear frame of reference to properly understand the scale. Light holds the title of the absolute swiftest phenomenon in the known universe, racing across space at a velocity of approximately 186,000 miles per second, which corresponds to roughly 300,000 kilometers every single second. To put that blistering speed in perspective, a beam of light could encircle the entire equator of the planet Earth, more than 7 distinct times in the span of just one single second. In the fleeting moment it takes for your fingers to make a sharp snap, a single particle of light could travel all the way from the streets of New York to the city of Tokyo, turn around and return to its starting point. Absolutely nothing in the grand catalogue of nature is capable of travelling faster than this cosmic velocity. Neither physical particles, nor raw energy currents, nor basic informational signals. This speed of light is not just an impressive number, it is the ultimate absolute speed limit of our universe, hard-coded directly into the fundamental fabric of reality by the unyielding laws of physics themselves. Yet, even when moving at this mind-boggling, incomprehensible velocity, it still requires that beam of light a total of 4 long years and 3 full months to complete the journey from our Sun to the vicinity of Proxima Centauri. Consider the staggering implications of that timeline for a moment. A stream of light photons departing from the surface of Proxima Centauri this very day, at this exact present instant, will not complete its journey to Earth until sometime well into the year 2030, which is more than 4 long years from our current moment. This extreme delay reveals the true staggering scale of the structural problem we are trying to solve. Now let us examine our actual, real-world technological capacity to cross such a monumental void. One of the most far-flung, distant mechanical spacecraft ever constructed by human hands is Voyager 1. This historic probe was originally launched into the skies on September the 5th, 1977, lifting off from the launch pads at Cape Canaveral, Florida. Since that day, Voyager 1 has been continuously drifting outward through the dark vacuum of space for nearly half a century. At this current moment, it sits at a greater distance from Earth than any other object ever manufactured by human civilization. In the month of August 2012, Voyager 1 achieved a historic milestone by officially crossing the heliopause, which is the turbulent magnetic boundary where the outward solar wind of our Sun finally gives way to the pristine interstellar medium. By crossing that line, it earned the distinction of becoming the very first human-engineered vehicle to successfully cross over into interstellar space. It remains out there in the deep freeze, still completely operational, still diligently broadcasting data back home across billions of miles of empty desolation, and it is travelling exceptionally fast by human standards. Voyager 1 is presently coasting at a rate of roughly 38,000 miles per hour relative to our central Sun. To our ears, a speed of 38,000 miles per hour sounds like an incredibly swift velocity. It truly is fast by every practical standard of measurement we utilise in our ordinary daily routines on Earth. For example, a standard commercial passenger airliner cruises through the sky at a modest speed of about 600 miles per hour, the absolute fastest land vehicle ever designed and driven. The rocket-powered Thrust SSC managed to clock a maximum top speed of roughly 760 miles per hour. Even a high-velocity bullet fired from a specialised high-powered rifle leaves the metal barrel travelling at an approximate speed of 2,000 miles per hour. When you compare these numbers, you realise that Voyager 1 is flying through the void 19 times faster than a speeding rifle bullet. It successfully traverses a distance of roughly 333 million miles with each passing year. That rate of travel is swift enough to transport a vessel from the surface of the Earth to the Moon in a span of less than 7 hours. It is a velocity fast enough to cross the Gulf to Mars in a matter of a few short weeks during a favourable, close planetary approach. However, look at what happens when you plug that exact same velocity into the mathematical equation required to reach our nearest stellar neighbour, Proxima Centauri. The mathematical reality is basic, simple, and utterly devastating to our dreams. Travelling at a continuous rate of 38,000 miles per hour across a vast distance of 25 trillion miles requires an agonising timeline of approximately 70,000 years. 70,000 years. Take a long moment to let that numbers-driven reality sink into your mind. By the time Voyager 1 finally makes its closest approach to the Proxima Centauri system 70 millennia from now, assuming it were even pointing in that precise directional vector, human civilization as we know it today will almost certainly be completely unrecognisable. And remember, Proxima Centauri is merely our immediate neighbour, the absolute closest star to our solar system. If your ambition was to travel to Sirius, which shines as the single brightest star visible in our nocturnal sky, the total duration of the trip would stretch to about 150,000 years at Voyager's current pace. Sirius is situated at a distance of 8.6 light-years away from us. If you aimed for Betelgeuse, the massive red supergiant star that maps out the prominent shoulder of the Orion constellation, you're looking at a distance of roughly 550 light-years. A Voyager-class space probe launched toward that destination today would not arrive before our own Sun completely exhausts its primary hydrogen fuel reserves, swells into a destructive red giant star, and obliterates the inner planets of our solar system, including Earth itself. The stark engineering reality of our situation is completely brutal. It is fundamentally impossible to slowly inch your way across the galaxy to the stars by simply attempting to construct slightly larger or marginally faster chemical-fueled rockets. The core problem we face is not that our mechanical engineers are failing to build sufficiently powerful rocket engines. The problem is the absolute law of physics itself. Every single rocket engine ever conceived or manufactured operates on the exact same underlying physical mechanism. You must carry mass in the form of fuel inside the ship. You ignite and burn that fuel, and the high-speed expulsion of the exhaust gas out the back provides the necessary forward thrust. But that fuel itself possesses mass. Because it has mass, that massive fuel load must be accelerated right along with the structural weight of the spacecraft itself. This reality introduces a harsh catch. You are forced to add even more fuel simply to push the weight of the fuel you already added, which in turn increases the total mass of the vehicle, requiring yet another layer of fuel to accelerate that added weight. This mathematical relationship is completely exponential rather than linear. It is universally referred to by aerospace engineers as the tyranny of the rocket equation, and it has acted as the ultimate bane of space travel since its very inception. The historic Saturn V rocket, which successfully propelled human astronauts to the Moon during the celebrated Apollo lunar program, burned through a staggering 3,000 tons of heavy fuel in its massive first stage alone. That is 3 million kilograms of refined kerosene and liquid oxygen completely consumed and blasted out the exhaust nozzles in a duration of just 2.5 minutes. All of that immense mountain of fuel, all of that crushing physical mass, and all of that astronomical financial expense was required simply to propel a tiny metal capsule housing 3 human beings a mere 250,000 miles away to our local moon. Now let us scale that exact same equation up to interstellar proportions. Proxima Centauri is situated 100 million times farther away from us than the moon is. If you attempted to utilize standard chemical-powered rockets to reach Proxima Centauri within the span of a single human lifetime, you would need to burn more fuel than currently exists on the entire planet Earth. That statement is not a hyperbolic exaggeration. The actual, precise mathematical calculation reveals that you would need to extract and burn more hydrocarbons than could ever be pumped from every oil deposit, every natural gas pocket, and every scrap of organic compound on our entire world. And even that planetary supply would fall woefully short of the requirement. You would be forced to travel to the outer solar system and harvest vast oceans of hydrocarbons directly from the thick atmospheres of gas giants like Jupiter and Saturn. You would have to systematically strip every single organic molecule away from every orbiting asteroid and icy comet in the entire solar system. Even if you successfully accomplish that solar system-wide mining operation, the numbers still refuse to work. The unyielding math of the rocket equation does not care how much raw fuel you manage to accumulate. It cares exclusively about the stark mathematical ratio between the mass of the fuel and the mass of the actual payload you are trying to deliver. And when you attempt interstellar travel using basic chemical propulsion, that required ratio explodes into entirely impossible, astronomically absurd values. Spacecraft engineers have been completely aware of this brick wall since the 1950s, which explains why every single serious scientific proposal for crossing interstellar space has tried to completely sidestep and abandon chemical rocket propulsion from the very start. One of the earliest radical ideas to emerge was nuclear pulse propulsion. This bold concept, which was systematically developed throughout the 1950s and 1960s under the classified designation Project Orion, involved detonating a continuous sequence of atomic bombs behind an exceptionally massive starship, allowing the vessel to literally ride the resulting nuclear shockwaves forward. Each individual atomic explosion would slam violently against a colossally thick steel pusher plate mounted to the rear of the ship, which was connected to the crew quarters by massive heavy-duty mechanical shock absorbers that would smooth out the acceleration. It is an aggressive, brute force engineering approach that sounds entirely insane on its face, and it probably is, but the underlying physics of the concept are entirely sound. Nuclear fission explosions release vastly more raw energy per unit of mass than can ever be achieved by any form of chemical reaction. In pure theory, a starship propelled by a nuclear pulse drive could successfully accelerate up to a few percentage points of the absolute speed of light. If a ship could travel at just 3% of the speed of light, the journey to Proxima Centauri is transformed into a 140-year voyage rather than a 70,000-year nightmare. While that is still significantly longer than a single human life cycle, it brings the mission into the plausible realm of generation ships, where the descendants of the original crew would eventually arrive at the destination. However, the practical, real-world obstacles facing Project Orion are absolutely enormous. You would be required to pack and systematically detonate thousands of nuclear warheads just meters from your ship. The required weight of the radiation shielding would be completely massive, adding immense dead weight to the vehicle. Furthermore, the political, ethical, and environmental fallout of launching a massive ship packed with atomic bombs from the surface of the Earth is almost certainly insurmountable, which explains why such a vehicle has never been built. Controlled nuclear fusion propulsion represents a separate, cleaner approach. Instead of splitting heavy atoms via fission, a fusion engine would burn isotope forms of hydrogen fuel in the exact same manner that active stars do, forcibly fusing light elements together into heavier ones and capturing the immense amounts of kinetic energy released in the process. A fusion-powered rocket engine would be drastically more efficient than any chemical system and vastly cleaner than a fission-based pulse drive. However, the human race has still not mastered the basic challenge of maintaining controlled nuclear fusion even in massive stationary power plants on solid ground. Successfully engineering a compact, lightweight fusion reactor that can reliably operate in the unforgiving, highly hostile vacuum of deep space is a milestone that sits several decades away at the absolute minimum. If fusion is a leap forward, antimatter propulsion represents the absolute theoretical maximum of fuel efficiency. When normal matter comes into physical contact with its corresponding antimatter counterpart, the two substances annihilate one another completely, converting 100% of their combined physical mass directly into pure, raw energy. According to the terms of Albert Einstein's famous mathematical equation, EMC2, absolutely nothing in the laws of physics can release more energy per unit of mass than this total matter-antimatter annihilation process. An antimatter-catalyzed rocket engine could theoretically possess the power to accelerate a starship to a highly significant double-digit fraction of the speed of light, But the problems here are similarly staggering. Antimatter simply does not exist naturally within our universe in any useful or harvestable quantities. Every single individual atom of antimatter must be painstakingly manufactured from scratch inside multi-billion-dollar particle accelerators at an absolutely enormous cost of electricity. Our current global production rates for antimatter are measured in mere billionths of a single gram per year. Trying to accumulate enough antimatter fuel to propel a true interstellar mission would require an amount of time that vastly exceeds the duration of the voyage itself. Additionally, the challenge of safely storing and containing antimatter inside a magnetic vacuum without allowing it to ever touch the ordinary matter walls of its fuel tank and instantly explode remains an entirely unsolved engineering nightmare. This brings us to solar sails, which represent a completely inverted philosophy of space travel. Instead of forcing a starship to carry heavy fuel tanks along with it, a solar sail vehicle utilises the continuous physical pressure exerted by ambient sunlight or incredibly powerful stationary laser beams to achieve acceleration. Photons of light carry a small but real amount of momentum, and an exceptionally large ultra-reflective fabric sail can be pushed through the void by these photons in the exact same manner that a traditional maritime sailboat is propelled across the ocean by the wind. The ambitious Breakthrough Starshot initiative, which was originally funded by billionaire tech investor Yuri Milner and enthusiastically supported by world-renowned scientists like Stephen Hawking prior to his passing, proposed utilising a massive ground-based array of ultra-powerful lasers to beam energy at tiny gram-scale microprobes equipped with high-tech light sails. The operational blueprint calls for accelerating these tiny feather-light chips to an incredible 20% of the speed of light. At that blistering velocity, these microprobes could cross the interstellar void to Proxima Centauri in roughly 20 years, snapping close-up photographs and broadcasting the scientific data back to Earth via compact onboard laser systems. It is an incredibly inspiring project that may very well succeed for tiny unmanned scientific instruments, but it simply does not scale up to human-crewed missions. A reflective light sail large enough to capture enough laser energy to push a massive starship containing human habitats, life support systems and supplies would need to stretch hundreds of miles across. Furthermore, the stationary laser array required to accelerate such a massive structure would demand a continuous energy output equivalent to a massive, highly significant fraction of the entire electrical power generation capacity of the modern world. While each of these innovative engineering approaches claws us a little bit closer to achieving real interstellar capability, and each represents a genuine hard-won advancement in our understanding of propulsion physics, none of them actually succeeds in breaking through the ultimate glass ceiling. That ultimate ceiling is the absolute speed of light itself. Moving at roughly 186,000 miles per second, or 300,000 kilometers per second, this limit is not merely a high velocity that we have failed to surpass due to a lack of better mechanical engineering or clever designs. It is a fundamental structural law of nature woven directly into the geometric tapestry of space and time itself. In the year 1905, Albert Einstein published his historic paper outlines the theory of special relativity. Among its various insights, this theory mathematically proved that no physical object possessing mass can ever be accelerated up to the exact speed of light. The core reason for this barrier is that as any object increases its velocity and approaches light speed, its effective, apparent relativistic mass begins to experience a dramatic increase. The closer you get to that ultimate cosmic velocity, the more energy you must inject simply to gain the next single mile per hour of speed. When a ship reaches 99% of the speed of light, its apparent physical mass has grown by a factor of 7 compared to its mass at rest. If you push it further to 99.9% of light speed, its effective mass explodes by a factor of 22. To successfully bridge that final fraction and actually touch the speed of light would require an absolute infinite amount of energy. Because infinite energy does not exist anywhere in our physical reality, nothing that possesses mass can ever reach or exceed the speed of light. This is not a temporary technological limitation that we can innovate our way out of by creating better rocket boosters or discovering exotic new metal alloys. It is a permanent rule built into the structural geometry of our universe. The speed of light is far more than a mere travel velocity. It represents the precise speed at which causality itself propagates through reality. It is the absolute maximum rate at which any piece of information or cause and effect relationship can move from one coordinate in space to another. The cosmic speed limit appeared to be completely absolute, or at least that was the unquestioned consensus of global science, until a brilliant young physicist working in Wales dared to ask a completely different kind of question. In the year 1994, Miguel Alcubierre was a 28-year-old theoretical physicist conducting postdoctoral research at the University of Wales in Cardiff. Originally trained at the National Autonomous University of Mexico before pursuing his advanced academic career in Europe, Alcubierre also happened to be an avid fan of science fiction, particularly the classic television series Star Trek. For anyone unfamiliar with the franchise, Star Trek is a seminal sci-fi show that originally debuted in the 1960s. The iconic starships depicted in the show routinely traverse the galaxy at speeds vastly exceeding the velocity of light by utilising a fictional propulsion system known as a warp drive. The characters frequently discuss travelling at warp 2, warp 5 or warp 9, blistering travel rates that allow them to cross immense interstellar voids in a matter of a few days or hours, rather than wasting entire generations in transit. Of course, the television writers never provided a real, working scientific explanation for how a warp drive actually operated. It was purely an entertaining narrative device designed for science fiction storytelling, not established science fact. Because of this, the vast majority of mainstream physicists completely dismissed the entire concept of warp travel as pure childish fantasy. After all, Einstein's equations clearly stated that travelling faster than light was an absolute physical impossibility. However, Alcubierre decided to approach the fictional concept as if it were a highly complex physics homework problem. He sat down at his desk with Einstein's field equations, which form the absolute mathematical bedrock of general relativity, the profound theory that explains the force of gravity not as a pulling force, but as the geometric curving and bending of spacetime by mass and energy. Alcubierre put a highly specific, revolutionary question to those mathematical equations. He wanted to find out, what exact structural shape would the fabric of spacetime need to adopt in order for a localized region within it to move across the universe faster than the speed of light, without any physical object located inside that specific region actually accelerating past local light speed relative to its surroundings. At its initial glance, this line of questioning sounds like blatant semantic cheating, as if he were trying to find a clever way to travel faster than light without technically moving faster than light. But as Alcubierre dug into the math, he realised that there was a massive overlooked loophole residing inside Einstein's historic equations that no physicist had ever seriously investigated in this context. Einstein's absolute cosmic speed limit applies strictly to physical objects moving through the pre-existing fabric of space. Crucially, the equations say absolutely nothing about a speed limit on the movement of space itself. There is a profound fundamental difference between these two concepts. When we state that nothing can exceed the velocity of light, we are explicitly stating that no object can move through the spatial fabric of spacetime faster than that limit. A chemical rocket accelerating away from a launch pad, a subatomic particle being slammed around a magnetic particle accelerator, or a radio wave broadcasting through the atmosphere are all distinct physical objects or energy waves propagating through the medium of space. Einstein's unyielding mathematics firmly prohibit every single one of them from ever crossing that light speed threshold. However, Einstein's equations also comprehensively describe how space-time itself is a dynamic, flexible entity that can warp, curve, contract, stretch, and actively expand. And there is absolutely no speed limit whatsoever dictated for how fast space itself can change its shape. In fact, we possess ironclad observational evidence that space can move faster than light because we can look through telescopes and actively watch it happening right now. The universe as a whole is undergoing a continuous cosmic expansion. Distant galaxies are steadily receding away from our position on Earth. And the further away a galaxy is located, the faster it appears to be moving away from us. When we look out to a specific threshold distance, roughly 14 billion light years away from Earth, we find galaxies that are actively receding away from us at velocities that vastly exceed the speed of light itself. This superluminal motion does not happen because those distant galaxies are physically flying through their local space at impossible speeds. Rather, it occurs because the actual space that exists between our galaxy and those distant systems is continuously stretching out. To visualize this, imagine a group of tiny ants walking across a highly stretchable rubber sheet. If you violently pull the edges of the rubber sheet, the ants will rapidly separate from one another. This separation does not happen because the ants are running away from each other on their own legs. It happens because the underlying rubber sheet itself is expanding in size, and the ants are simply riding along on top of that expansion. There is no physical limit to how fast that underlying rubber sheet can be stretched. This cosmic phenomenon is formally known as the metric expansion of space, and it has been completely confirmed by decades of highly precise astronomical observations and measurements. Alcubierre analysed this profound loophole and asked the next logical question. If the stretching of space can carry entire galaxies apart at velocities that exceed the speed of light, why couldn't we use that exact same mechanism to transport a human spacecraft across the stars? Could we theoretically engineer a highly localized pocket of space-time that would forcefully compress the fabric of the universe directly in front of a ship, while simultaneously stretching and expanding space directly behind it, allowing the vessel to surf across the galaxy on the resulting wave? He began working through the complex mathematics with meticulous care. The framework of general relativity maps out the structure of space-time by utilizing an entity called a metric, which functions as a comprehensive mathematical blueprint or recipe for calculating distances and times across a given coordinate system. Different metrics are used to describe completely different shapes of warped or flat spacetime. For example, the metric used to describe completely flat, empty space devoid of any gravity is known as the Minkowski metric. The mathematical metric used to calculate the curved spacetime around a massive, non-rotating object like a star is called the Schwarzschild metric, which outlines standard gravity. If you are dealing with the twisted, dragging spacetime around a rapidly rotating black hole, you must utilize the Kerr metric. Every single one of these metrics represents a mathematically valid solution to Einstein's complex field equations. Alcubierre sat down and constructed an entirely new metric from scratch. a metric that explicitly described a localized moving bubble of space. Inside the exact center of this bubble, the Minkowski metric applies, meaning the space is perfectly flat and calm. Within this central pocket, space behaves in a completely normal fashion. Time ticks forward at its standard rate, and light travels at its ordinary speed. An astronaut sitting inside the center of this bubble would feel absolutely nothing unusual whatsoever. No crushing g-forces, no artificial weight, and zero physical acceleration. Outside the boundaries of this moving bubble, the metric is also completely flat, seamlessly matching the resting geometry of the wider universe. However, right at the boundary wall of the bubble, Alcubierre's new metric does something truly extraordinary. On the front, leading edge of the bubble wall, the fabric of space is forced to contract sharply and violently. The components of the metric alter in a precise way that dramatically compresses physical distances directly in front of the bubble's path. Simultaneously, on the back, trailing edge of the bubble wall, the spatial fabric expands, just as sharply and violently. Distances are stretched out rapidly behind the bubble. The localized warp bubble itself literally rides forward on this newly engineered geometric wave. From an outside observer's perspective, looking on from a safe, stationary vantage point in the wider universe, this newly engineered warp bubble would appear to translate cleanly through the vast void of space at any arbitrary speed whatsoever. It could be designed to move significantly slower than the speed of light. It could match the speed of light precisely, or it could coast along at dozens of times faster than the speed of light. The overarching laws of the universe place absolutely no restrictions or upper limits on the speed at which this structural distortion can move across the cosmos. Yet, look at the situation from the internal perspective of a human traveller sitting calmly inside the centre of this bubble. From their point of view, absolutely nothing is moving at all. The vehicle is completely at rest, safely enclosed within an isolated pocket of perfectly flat, calm and undisturbed Minkowski spacetime. This structural pocket changes its coordinates in the universe exclusively because the space surrounding it is constantly reconfiguring its geometry. The starship does not undergo any form of physical acceleration. It is completely immune to the standard time dilation or length contraction effects of special relativity, and it never requires massive amounts of kinetic energy in the traditional mechanical sense. Instead of accelerating through the universe, the vessel is literally surfing a localized directional wave engineered directly into the geometry of space-time itself. Miguel Alcubierre officially shared this elegant mathematical revelation with the global scientific community in May 1994, publishing his findings in the peer-reviewed journal Classical and Quantum Gravity. The paper was given the title The Warp Drive, Hyperfast Travel Within General Relativity. It was a concise document, spanning only 8 pages in length, but it was incredibly dense, packed with complex tensor calculus equations and geometric diagrams outlining exactly how the various components of the metric behaved. Almost immediately, it became one of the most widely cited and hotly debated papers in theoretical physics of that entire decade. When it first appeared in print, the global physics community reacted with an intense mixture of profound excitement and deep, fundamental skepticism. The excitement stems from the fact that the math was completely unassailable. Alcubierre's metric was a genuinely valid, mathematically sound solution to Einstein's field equations. It was not a clever parlour trick, an oversight, or a basic mathematical error. It genuinely and accurately described a real space-time geometry where a localized bubble could move across interstellar distances faster than light without violating special relativity locally. Einstein's absolute speed limit was completely respected. Inside the bubble, light always travelled at standard light speed relative to the ship, and outside the bubble, light behaved normally as well. No physical particle was travelling through space faster than light, yet the bubble, as an entire unit, was fully capable of crossing vast interstellar gaps, faster than a beam of light travelling along a standard unwarped path. The deep scepticism, however, arose from what the solution required to actually build in the physical world. Alcubierre's theoretical warp bubble demanded something that no experimental physicist had ever observed or manufactured. It required the existence of exotic matter. Specifically, the metric could only function if it were supported by matter or energy fields that possessed a negative energy density. To understand why this is such a monumental problem, let us look at how energy behaves in our daily lives. Ordinary matter, which constitutes everything you can see, touch, or interact with in the universe, possesses a positive mass and a positive energy density. A simple rock has positive energy, a human body has positive energy, and a massive gas cloud drifting between the stars has positive energy. Because of this positive energy density, ordinary matter naturally curves spacetime inward, creating the attractive force we experience as standard gravity. But to create the opposite effect, to force the fabric of space to violently expand and stretch out behind a starship, you require the exact mathematical opposite. You need a substance that pushes spacetime away, acting as a form of repulsive gravity. This requires negative energy density, a bizarre concept where a region of space contains less than zero energy. For decades, many mainstream physicists believed that negative energy density was a physical impossibility, a mere mathematical artifact that could never exist in our real universe. Without a mechanism to generate vast quantities of this exotic matter, Alcubierre's warp drive was destined to remain nothing more than a beautiful, intriguing mathematical curiosity on paper, forever locked away from reality. Yet, as the years rolled on, other brilliant physicists began to carefully poke and prod at Alcubierre's equations, looking for clever ways to modify the geometry and reduce these seemingly impossible physical requirements. Throughout the late 1990s and into the 2000s, a series of important refinements were made. Researchers discovered that by altering the thickness of the warp bubble's wall, or by changing the overall shape of the bubble from a perfect sphere to a torus or donut shape, they could dramatically lower the total amount of negative energy required to sustain the field. Initially, Alcubierre's calculations suggested that a warp drive would require an amount of negative energy equivalent to the total mass of the entire observable universe. Later, physicist Chris van den Broek demonstrated that by making the bubble incredibly small on the outside while maintaining a larger volume on the inside, the energy requirement could be cut down significantly. Subsequently, Harold Sonny White, working out of NASA's EagleWorks laboratories, optimized the geometric configuration even further, showing that a toroidal warp bubble could potentially be fueled by an amount of exotic matter roughly equivalent to the mass of a small spacecraft like the Voyager probe itself. While this was a massive step forward, dropping the requirement from cosmic scales down to planetary or vehicular scales, it still did not solve the fundamental problem. You still needed a substance with negative energy density, and nobody knew how to harvest it in bulk. This long-standing roadblock is exactly why the scientific landscape shifted so dramatically in the early 2020s. A dedicated group of international researchers and independent physicists formed an organisation known as Advanced Physics, or the Applied Physics Team, with the explicit goal of moving warp drive research away from highly speculative science fiction and into the realm of rigorous classic engineering. This was a unique research collective, funded largely by private tech investors who were entirely comfortable backing highly speculative, long-term foundational projects without the intense political or bureaucratic pressure that often plagues traditional university grants or government institutions. If the work did not yield immediate practical results for a decade, the investors completely understood that they were funding basic exploratory research with highly uncertain timelines. In February 2021, two prominent members of this applied physics group, Alexei Bobrik and Gianni Martire, shook up the field by publishing a landmark paper. The paper was given the clear title Introducing Physical Warp Drives, and it was accepted and published in Classical and Quantum Gravity, the exact same respected peer-reviewed journal that had carried Alcubierre's foundational work nearly 3 decades prior. What Bobrik and Martyr accomplished in this paper was fundamentally different from the work of previous researchers. Instead of simply dreaming up a specific new warp drive design, or slightly tweaking a metric component, they stepped back to construct a comprehensive general framework for classifying all mathematically possible warp drive spacetimes. They essentially built a taxonomy, a rigorous, systematic method for organising and analysing the entire mathematical solution space of general relativity as it relates to warp fields. The core insight at the heart of their paper was incredibly elegant in its simplicity. They proved that every single warp drive design ever conceived, without a single exception, is structurally composed of 3 distinct geometric regions. First, there is an asymptotically flat region situated far away from the spacecraft. This is ordinary unwarped space, the standard cosmic vacuum that we live in, completely flat or nearly so, matching the baseline geometry of the universe, far from any crushing gravitational sources. Second, there is a passenger region positioned at the absolute centre of the system. This interior region is also perfectly flat. This is the safe haven where the human crew lives, where the physical hull of the ship and all its complex mechanical equipment sit, where onboard clocks tick forward at a completely normal rate, and where the laws of physics behave exactly as you would expect in daily life. Third, there is a warping region that acts as a boundary layer sandwiched between the other two. This is the active shell of intensely curved spacetime that does all the heavy lifting. It is the specific zone where the metric smoothly transitions from the flat interior pocket to the flat exterior universe, creating the intense space compression directly ahead of the path and the corresponding space expansion directly behind it. Every warp drive proposal in history, from Alcubierre's original 1994 bubble to Van den Broek's microscopically shrunken bubble to Harold White's optimized torus, fits perfectly into this universal 3-region framework. The structural differences between various designs simply come down to how this middle warping region is shaped, what specific kind of matter or energy fields fill its volume, how thick or thin the shell is configured, how sharply the space within it is curved, and how the bubble boundaries interface with the surrounding unwarped universe. By mapping all existing and hypothetical warp drives into this single unified structural classification scheme, Bobrik and Marta were suddenly able to ask systematic, comprehensive questions about the physics of space propulsion. Which specific regions of the design space had been heavily explored by past researchers, and which areas remained completely untouched? What mathematical constraints applied universally to all designs, and what features were merely optional stylistic choices? As they systematically analysed the map, they discovered large territories of solutions that no previous scientific paper had ever investigated. One of the most promising and overlooked territories they identified was the subluminal warp drive. For the previous 30 years, almost all academic research into warp fields had focused exclusively on superluminal designs, bubbles moving faster than the speed of light, Because crossing the light barrier was widely seen as the whole point of the exercise, the general consensus was that if you were going to go through the immense trouble of violating causality and violently bending the fabric of spacetime, you might as well go all the way and beat the ultimate cosmic speed limit. However, Bobrick and Martyr pointed out a massive blind spot. Subliminal warp drives, which describe space-warping bubbles travelling slower than the speed of light, might be vastly easier to construct in the physical world. Crucially, they discovered that these slower-than-light warp bubbles might completely satisfy standard energy conditions, meaning they could circumvent the violations that exotic matter introduces. In short, subliminal warp drives might not require an ounce of negative energy density to function, and even though they remain below the speed of light, such vehicles would still be mind-bogglingly useful for space exploration. A subliminal warp bubble cruising through space at 90% of light speed does not break Einstein's cosmic speed limit, but it would possess the capability to cross our entire solar system in a matter of a few hours, travel the immense distance to Proxima Centauri in under 5 years, and complete the entire journey without ever subjecting the human crew inside to any acceleration forces or crushing g-forces whatsoever. Furthermore, their paper mathematically proved an important physical theorem that had never been stated clearly in previous literature. They demonstrated that any warp drive, regardless of its specific geometric configuration or design quirks, is effectively a shell of matter that has been set in motion. This material shell moves through the vacuum of space exactly like any other ordinary physical object, which means it still requires some external or internal propulsion system to physically accelerate it up to its desired cruising velocity. This was a profound realization. A warp bubble does not magically eliminate the need for traditional rockets or propulsion drives. Instead, it completely changes what the rocket propulsion system is actually pushing. In a standard space mission, a rocket engine must push the spacecraft directly, accelerating the fragile human crew and the heavy cargo, which subjects them to intense mechanical forces. In a warp drive system, the propulsion mechanism accelerates the entire bubble shell itself, and the bubble smoothly carries everything nestled inside its flat interior pocket without transmitting any physical forces or inertial stresses to the crew quarters. This insight completely reframed the entire warp drive problem for the scientific community. A warp drive was no longer viewed as a magical, physics-defying device. It was understood to be a highly specific, carefully structured space-time geometry that, once set in motion by conventional means, carried an interior region of flat space along for the ride. The internal crew members feel absolutely zero g-forces because they are never undergoing local physical acceleration. The external universe observes the bubble moving across coordinates, but getting that bubble up to speed in the first place remains firmly bound to the rules of conventional propulsion physics. The Bobrick-Martyr framework rapidly became the definitive standard reference for warp drive research moving forward into the decade. Virtually every serious physics paper published after 2021 cited their work heavily. Their classification scheme became a universal language to describe new designs, and their focus on subliminal configurations opened up an entirely new research direction that had been largely ignored for a generation. The applied physics team did not stop there. They had successfully classified the structural parameters of the problem, and now they needed to find a specific, workable solution. In the year 2024, they did exactly that. Their breakthrough was officially published in Classical and Quantum Gravity, appearing in Volume 41, Number 9, as Articles 095013 on April 29, 2024. The historic paper bore the title Constant Velocity Physical Warp Drive Solution. The author list represented the entire core of the applied physics collective, pulling their talents together focused entirely on a single mathematical breakthrough. Lead author Jared Fuchs, alongside co-authors Christopher Helmrich, Alexei Bobrick, Luke Sellers and Gianni Martir. What this paper claimed to achieve was nothing short of extraordinary. The authors presented a complete, mathematically rigorous warp drive solution that eliminated the need for exotic matter entirely, proving that a stable warp bubble could be constructed using nothing but regular positive energy matter, provided it was arranged in a precise, highly calculated geometric shell. This 2024 solution finally bridged the immense gap between theoretical fantasy and real-world engineering possibility. It proved that if you are content to travel just under the speed of light, you do not need to discover new, non-existent particles or invent ways to manufacture negative energy. The paper detailed exactly how a shell of ordinary matter, compressed to extreme densities comparable to the material found inside a neutron star, could be manipulated using powerful gravitational and electromagnetic fields to curve the space around it into a stable, moving bubble. While the material requirements are still monumentally difficult, demanding engineering capabilities that humanity will not possess for a very long time, the crucial takeaway is that the physics itself is fully cooperative. It changed the entire conversation from "this is fundamentally impossible according to the laws of nature" to "this is an incredibly difficult engineering challenge that we can eventually learn how to solve." To fully appreciate why this shift is so monumental, we must contrast it with other theoretical shortcuts through the universe, most notably wormholes. For decades, wormholes have been popularized in science fiction as the ultimate method for instantaneous cosmic travel. In the late 1980s, renowned physicist Kip Thorne famously mapped out the physics of what he called traversable wormholes, tunnels through the fabric of spacetime that could connect two widely separated points in the universe, allowing a ship to enter one end and instantly step out thousands of light years away. However, Thorne's equations revealed that, to prevent a wormhole from instantly snapping shut, the throat of the tunnel must be lined with vast quantities of exotic matter possessing negative energy density. Look closely at the differences in structural stability between these two concepts. A wormhole requires exotic matter not just to be built, but to actively resist the crushing inward pull of gravity. The negative energy inside a wormhole throat is structural. It is constantly fighting an active, dynamic battle to keep the tunnel open against a relentless gravitational pressure that wants to pinch it out of existence. If that exotic matter supply fluctuates or is disrupted for even a fraction of a microsecond, the entire wormhole throat instantly collapses, completely crushing any spacecraft caught inside into an infinitely dense singularity. Furthermore, the sheer quantity of exotic matter required to keep a human-scale wormhole open is utterly astronomical, with estimates suggesting you would need a shell of negative energy equivalent to the total mass of a large planet just to maintain a tunnel a few miles wide. A warp drive, especially in light of modern subluminal developments like the Fuchs solution, operates on a fundamentally more stable and forgiving physical foundation. In a warp drive system, the matter configuration forms a shell around the vehicle, and once that shell is properly shaped and accelerated to its cruising speed, it simply maintains its geometric profile as it travels. It is not constantly fighting an internal structural collapse in the same violent manner as a wormhole throat, and by shifting our focus to subluminal velocities, we completely erase the exotic matter requirement from the blueprint, allowing us to build the entire system out of standard positive energy matter. However, even if we completely sidestep the need for exotic matter by keeping our warp bubbles below the speed of light, theoretical physicists have uncovered another terrifying hurdle built into the quantum fabric of reality: the problem of Hawking radiation. When a warp bubble moves through space, the intense curvature at its boundary walls can create a physical phenomenon known as a horizon, which is very similar to the event horizon of a black hole. In quantum field theory, when a horizon is formed in spacetime, it naturally begins to separate virtual particle pairs that are constantly popping into existence in the vacuum. This separation causes the horizon to steadily emit a stream of high-energy particles known as Hawking radiation. If a warp bubble is accelerated past the speed of light, this horizon becomes completely absolute, cut off from the interior of the ship. Quantum calculations show that the resulting build-up of Hawking radiation along the superluminal boundary would be completely catastrophic. The horizon would essentially transform into an incredibly intense cosmic furnace, blasting the spacecraft interior with an unmitigated flood of deadly, high-energy radiation that would instantly vaporize the hull and kill the crew inside. This is not an engineering challenge that can be overcome by inventing thicker radiation shields or utilizing stronger hull materials. It is an intrinsic response of quantum fields reacting to superluminal space-time curvature. But this is exactly where the subluminal escape clause becomes so profoundly important for modern mission planners. If the warp bubble is designed to travel slower than the speed of light, a true absolute event horizon never actually forms along its boundary walls. And without the formation of a true horizon, the quantum vacuum fields are never forced to emit Hawking radiation. This represents yet another massive scientific reason why subluminal warp drives, such as the solution published by the Fuchs team, are vastly more practical and physically viable than any faster-than-light design. They completely circumvent the deadly radiation problem by remaining safely below the threshold where quantum horizons manifest. They avoid the killer physics entirely by staying within the cosmic speed limit, while still delivering all the incredible propulsion benefits of a warp field. The physical limitation introduced by the horizon problem doesn't definitively prove that a warp drive is fundamentally impossible to build in our universe. Rather, it clearly demonstrates that superluminal travel, propelling a space-warping bubble faster than the speed of light, comes packed with severe quantum penalties that nature might simply refuse to let us bypass. By shifting our perspective down below the light speed threshold, however, we enter a completely different physical landscape, where the mathematical solutions become exceptionally well-behaved and physically realistic. This is precisely why modern theoretical physics has pivoted so heavily toward the subluminal escape clause, recognizing that a slower-than-light space-warping vessel offers an elegant path forward. If the engineering shell moves through coordinates at an immense speed that remains strictly less than the velocity of light, a true absolute event horizon never actually forms across its leading or trailing boundaries, because there is no absolute horizon to savour causal contact with the rest of the cosmos. The surrounding quantum vacuum fields are never subjected to the violent topological tearing that forces them to emit an unmitigated torrent of Hawking radiation. This means the human crew nestled safely inside the central flat region can complete an entire interstellar voyage without ever worrying about being vaporized by a self-generated cosmic furnace. Yet, even if a subluminal warp drive completely neutralizes the lethal threat of Hawking radiation, theoretical physicists navigating this field have identified another terrifying obstacle that emerges directly during the voyage itself. This problem involves the physical matter and stray particles that the moving bubble inevitably encounters as it ploughs its way through the vast cosmic void. From our perspective on Earth, interstellar space looks like an absolute pristine vacuum of perfect emptiness. But in reality, the interstellar medium is thinly populated by a sparse distribution of matter drifting between the star systems. On average, every single cubic centimetre of space throughout our local region of the galaxy contains roughly one stray hydrogen atom. Helium atoms are also scattered throughout the void, though they are significantly rarer alongside occasional microscopic grains of silicate cosmic dust, stray electrons, wandering ions, and high-energy cosmic rays blasting outward from distant ancient supernovas. For a conventional spacecraft travelling at standard chemical or ion velocities, like the Voyager probes, this incredibly sparse medium is entirely negligible. Voyager 1 has been cruising directly through this thin cosmic gas for nearly 50 years without experiencing any significant structural friction or structural degradation from the surrounding atoms. But everything changes completely when you calculate what happens when a highly curved warp bubble ploughs through this exact same sparse environment at extreme velocities. The exact underlying physics of this interstellar interaction was painstakingly mapped out in a detailed 2012 academic paper written by a team of brilliant researchers, including Brendan McMonagle, Geraint Lewis, and Philip O'Byrne. The research team sat down with the equations of general relativity to answer a simple yet profoundly alarming question. What exactly happens to the ambient matter of the interstellar medium when a space-warping bubble sweeps through its location? The mathematical answers they uncovered were deeply unsettling for future interstellar explorers. As the warp bubble translates forward through space, the hydrogen atoms, stray ions, and cosmic dust particles sitting quietly in its path do not simply pass cleanly through the boundary walls to emerge harmlessly on the other side. Instead, because of the extreme geometric distortion at the front of the bubble, these particles become completely trapped. They get caught and held fast within the violently compressed geometry of spacetime, characterizing the leading edge of the vehicle. As the journey continues across the stars, the severe compression of spacetime continually acts upon these trapped particles, accelerating them to unimaginable relativistic energy levels. They can never escape the forward wall while the warp field is active. So they simply accumulate over time, steadily building up an increasingly dense, hyper-energetic reservoir of compressed matter that travels right along with the bubble shell. The longer the interstellar voyage lasts, the more matter the leading edge sweeps up, and the more dangerous this energetic reservoir becomes. A standard trip spanning several light years between close neighbouring stars would sweep up billions upon billions of cosmic particles, with each individual atom or grain of dust carrying an amount of kinetic energy that is directly proportional to the overall velocity of the moving bubble. This material build-up doesn't hurt the crew during transit because the passenger region at the centre remains perfectly flat, isolated and shielded from the extreme phenomena occurring at the boundary walls. The real catastrophe occurs when the spacecraft finally arrives at its intended destination and the propulsion system prepares to shut down the warp field. The moment the intense space-time curvature relaxes and the bubble dissipates back into the flat baseline geometry of the universe, the ship loses its grip on that massive reservoir of trapped matter. All those billions of hyper-accelerated high-energy particles are instantly released all at once, blasting outward from the ship's final position in a tightly focused, devastatingly concentrated beam of pure kinetic energy. Because of the forward momentum of the journey, this particle beam travels in the exact same direction the starship was heading, pointing directly toward the star system or planet the crew was attempting to visit. According to the rigorous calculations published by McMonagle and his colleagues, the sheer amount of energy unleashed within this narrow cone of destruction could be equivalent to the kinetic energy of hundreds of thousands of solar masses. It is a weapon of cosmic proportions generated entirely by accident as a byproduct of space travel. Anything unfortunate enough to be positioned within that narrow exit cone would be completely and utterly annihilated. A warp-capable starship arriving at a neighbouring solar-like Proxima Centauri wouldn't settle gracefully into orbit to begin a mission of peaceful scientific discovery. Instead, its arrival would completely materialise as an apocalyptic event, instantly sterilising the entire star system. Any planets caught directly in the path of the focus particle beam would have their atmospheres violently stripped away in an instant, their oceans boiled into space, and their rocky surfaces scorched down to the absolute bedrock, or possibly vaporised into clouds of expanding gas if the transit distance was long enough to accumulate a truly massive payload of interstellar matter. The starship itself would survive the shutdown completely unharmed because it sits safely behind the release point in its flat pocket of space. But the explorers would step out of their bubble only to find that they had accidentally destroyed the very world they crossed the galaxy to study. This cataclysmic arrival problem represents one of the most severe engineering and ethical challenges associated with high-speed warp metrics, forcing physicists to look for clever ways to modify the bubble design to bleed off these trapped particles safely before reaching a destination. Yet, long before an engineer can ever worry about how to safely park a warp ship without destroying a solar system, they must first confront the ultimate practical barrier that has loomed over this field since 1994, the generation and manipulation of negative energy fields. As we have seen, unless you utilise highly specific, modern subliminal configurations like the Fuchs solution, which require crushing matter densities, any standard attempt to expand and stretch the fabric of space behind a vehicle demands a region of negative energy density. For decades, the standard response from the mainstream scientific community was that less than zero energy was a mathematical fiction, a neat trick with negative signs in tensor calculus that could never correspond to anything real in the physical world we inhabit. However, nature has a fascinating way of revealing that things we assume to be completely impossible are actually occurring right under our noses in the quantum realm. Physicists eventually discovered that regions of negative energy density are not just theoretically allowable. They have actually been successfully generated and measured inside modern physics laboratories through a phenomenon known as the Casimir effect. First predicted in 1948 by the Dutch physicist Hendrik Casimir, this effect describes a bizarre, counterintuitive force that manifests at atomic scales due to the fundamental quantum nature of empty space. In classical physics, a vacuum is understood to be a state of absolute nothingness, a perfect void completely devoid of matter, light, and energy. But in quantum field theory, a vacuum is never truly empty. Instead, it is a dynamic, buzzing hive of activity, filled with zero-point energy fluctuations, where virtual particles and antiparticles are constantly popping into existence out of nothing, interacting for a fraction of a femtosecond, and then instantly annihilating each other to vanish back into the void. Hendrik Casimir realised that you could manipulate these omnipresent quantum vacuum fluctuations by placing two uncharged, highly reflective metal plates incredibly close together in a vacuum, separated by a distance measured in micrometers or nanometers. When you bring these two plates into such extreme proximity, you create a physical restriction on the behaviour of the quantum fields between them. The virtual photons popping into existence inside the tiny gap can only exist at specific quantized wavelengths that fit perfectly between the two solid walls, much like the discrete acoustic harmonics that can vibrate inside the string of a musical instrument. Outside the plates, however, there are absolutely no physical boundaries or restrictions, meaning virtual photons of every conceivable wavelength can pop into existence completely unimpeded, because there is a vast, infinite variety of particle wavelengths pushing against the outer surfaces of the plates, but only a restricted, finite number of wavelengths vibrating inside the narrow gap. A dramatic imbalance of quantum pressure is created. The outside vacuum pressure completely overwhelms the internal vacuum pressure, forcing the two metal plates to be physically pushed toward each other by an attractive force that has no origin in standard electromagnetism or classical gravity. The most profound realization to emerge from this phenomenon is what it implies about the energy state inside that tiny gap. Because the restriction of wavelengths means there are fewer quantum vacuum fluctuations allowed inside the gap than there are in ordinary unwarped empty space. The energy density between those two plates drops below the baseline value of the standard cosmic vacuum. In the language of modern physics, if we define the baseline energy of ordinary empty space as zero, then the restricted region inside a Casimir cavity possesses a total energy density that is mathematically less than zero. It is a genuine, physically verified pocket of negative energy density manufactured by human engineers using standard, everyday matter arranged in a clever geometric configuration. When experimental physicists successfully measured this subtle attractive force in high-precision laboratory tests during the late 1990s, it provided irrefutable empirical proof that negative energy density is a real, tangible property of our universe. This incredible experimental success immediately caused a massive wave of excitement to ripple through the warp drive research community. For the first time, scientists had hard proof that the exact substance required to fuel an Alcubierre warp bubble actually existed in nature and could be manipulated by human technology. This led to a critical question that dominated propulsion physics discussions for years. Could we simply harvest the negative energy generated inside these Casimir cavities, scale up the manufacturing process, and utilize it to construct a functional warp drive, or hold open a stable interstellar wormhole? When you run the numbers using our current technological capabilities, the answer to that question is an absolute, definitive, and unambiguous no. The fundamental problem is one of sheer, overwhelming scale. The amount of negative energy generated inside a standard laboratory Casimir cavity is infinitesimally tiny, almost completely lost in the noise of the macroscopic world. For example, if you take a pair of perfectly engineered reflective plates that are exactly 1 square metre in total surface area, and you separate them by a microscopic gap of exactly 1 micrometre, the total amount of negative energy produced within that entire volume is on the order of 10 to the negative 7th joules. That amounts to roughly 1/10,000,000th of a single joule of energy. To put that into an easily understandable perspective, that is significantly less energy than it takes for a single mosquito to flap its wings one time. Now, contrast that microscopic sliver of energy with the immense power demands outlined in standard warp drive blueprints. Even after decades of geometric optimization and clever structural refining, theoretical warp drive designs still call for an amount of negative energy that is measured in kilograms or tons of absolute mass equivalent. To understand exactly how massive that requirement is, we must look to Albert Einstein's most famous mass energy equivalence equation, E equals mc squared. According to this fundamental formula, a single kilogram of physical matter corresponds to an astronomical amount of raw energy, specifically about 9 times 10 to the 17th joules, the physical gap between the subatomic amounts of negative energy that a modern Casimir cavity can produce and the planet-shaping amount of negative energy that a Starship warp drive requires to expand spacetime is roughly 24 orders of magnitude. That is a factor of 1 trillion trillion. Trying to fuel an interstellar warp drive using the negative energy harvested from standard laboratory Casimir plates would be like trying to build a towering skyscraper using the atomic fragments of a single grain of sand. The scales are so utterly mismatched that the concept is completely unworkable as a direct engineering path. Furthermore, even if we could somehow dream up a method to manufacture these microscopic Casimir structures by the quadrillions to pool their energy together, quantum physicists have discovered that nature has built a set of strict, unyielding speed bumps directly into the laws of quantum mechanics to prevent anyone from accumulating vast reservoirs of negative energy. These restrictive laws are known as the quantum inequalities, and they were mathematically proven in the 1990s by two highly respected theoretical physicists, Larry Ford and Thomas Roman. Ford and Roman set out to investigate whether the laws of quantum field theory placed any fundamental boundaries on how negative energy could behave across space and time, and their discoveries dealt a severe mathematical blow to early warp drive enthusiasts. The quantum inequalities are rigorous mathematical theorems that prove negative energy, whenever and wherever it chooses to manifest in our universe, is always bound by a brutal cosmic trade-off. The theorems demonstrate that you can never simply create a large pool of negative energy and let it sit there quietly, indefinitely. Instead, the laws state that the more intense and concentrated the negative energy density is in a given region, the shorter the total amount of time it can physically persist before being overwhelmed by a corresponding flash of positive energy, and the smaller the physical volume of space it can occupy. It is a fundamental balancing act woven directly into the quantum fabric of reality. If you want to have a significant, highly concentrated amount of negative energy, you can only have it for a tiny, fleeting fraction of a microsecond, and it must be restricted to a subatomic region of space. Alternatively, if you want to sustain a region of negative energy over a longer, macroscopic period of time, across a larger volume, the intensity of that negative energy must drop to a nearly imperceptible microscopic value. What you can never have under these laws is a massive, highly concentrated amount of negative energy sustained indefinitely over a large macroscopic region of space, which is precisely the exact requirement needed to build and fly a standard Alcubierre warp drive. The quantum inequalities do not completely outlaw the theoretical existence of warp drives, but they make their physical construction extraordinarily difficult, effectively shutting the door on any simple engineering scheme to power a starship using negative energy extracted directly from standard quantum vacuum fluctuations. To build a classic faster-than-light warp drive, engineers would have to discover a massive physical loophole, a highly specific configuration of spacetime where these quantum inequalities either do not apply or where their restrictions are significantly loosened. Such exotic loopholes might theoretically exist. It is entirely possible that the elusive, currently unknown theory of quantum gravity, the holy grail of modern physics that seeks to seamlessly unify Einstein's general relativity with the chaotic rules of quantum mechanics, might modify or rewrite these inequalities in profound, unexpected ways at the Planck scale. Alternatively, new physics discovered beyond the standard model might eventually reveal entirely new types of quantum fields or exotic particles that possess unique properties capable of completely circumventing these structural constraints. But for the moment, all of these ideas remain purely speculative. We do not possess a validated working theory of quantum gravity, and our most advanced particle accelerators have yet to uncover any evidence of physics beyond the standard model that can assist with the industrial scale production of negative energy fields. The engineering required to build a traditional warp drive remains entirely aspirational, existing as an active and highly respected area of theoretical research, where small teams of dedicated scientists at elite universities and national laboratories continue to chip away at the mathematics. They are making steady, incremental progress, learning how to measure smaller and smaller quantum forces, and developing a vastly deeper understanding of how matter interfaces with the geometry of space. Yet, none of these efforts has yielded a practical mechanism for generating the vast reservoirs of negative energy required to construct a real-world warp drive or stabilise a cosmic wormhole. The engineering challenge is immense, and it may very well remain immense for centuries to come, meaning that on the longest possible timeline, the realisation of warp travel might not require entirely new, exotic physics, but rather an extraordinarily patient, multi-generational refinement of the physics we already understand. This realisation brings us to one of the most fascinating and deeply intriguing pieces of this entire cosmic puzzle. If warp drives are physically permissible under the laws of nature, and if advanced, highly intelligent alien civilizations existing elsewhere in the vastness of the universe have already solved these immense engineering challenges, it is highly probable that they are occasionally flying these space-warping vessels across the stars. And if they are operating these vehicles, and those vehicles occasionally suffer mechanical failures or catastrophic structural collapses, we might actually possess the technological capability to detect those distant failures right now from Earth. In July 2024, a team of brilliant researchers led by Katie Clough at Queen Mary University of London, alongside several international collaborators, published a groundbreaking paper in classical and quantum gravity that shifted the entire field of warp research into the realm of observational astronomy. The historic paper was given the evocative title, "What No One Has Seen Before: Gravitational Waveforms from Warp Drive Collapse." What Clough and her research team accomplished was to ask a brilliant, highly practical question that no serious academic paper had ever addressed before. What exactly happens when a functioning warp bubble fails? They weren't focused on cataloguing the specific mechanical or physical reasons why a bubble might break down, but rather on calculating the exact, mathematically precise observational signature that such a catastrophic failure would leave echoing across the fabric of the universe. The underlying setup for their research was straightforward and grounded in classical general relativity. A warp bubble is not a permanent, natural feature of the cosmos. It is a highly structured, artificially engineered region of spacetime that is held in a state of extreme curvature by a precise, highly calculated distribution of matter and energy fields. If that complex distribution ever becomes unstable, or if the generator system powering the ship suddenly suffers a critical malfunction, the entire warp bubble will instantly collapse. And as the team's calculations revealed, a warp bubble collapse is not a gentle, quiet event that fades away unnoticed into the background noise of space. It is an incredibly rapid, violently energetic, and profoundly catastrophic event. The intensely curved space-time geometry that was meticulously wrapped around the starship suddenly and violently snaps back to its flat, natural baseline state. In a fraction of a millisecond, all of the immense physical energy that was stored inside the severe curvature of that artificial metric is violently released into the surrounding universe. To model the exact dynamics of this violent snapping effect, Clough's team turned to the advanced tools of numerical relativity simulations. Numerical relativity is a highly specialised branch of computational physics that uses the world's most powerful supercomputers to solve Einstein's complex field equations step by step in dynamic, highly unstable environments where analytic pen and paper math completely breaks down. This is the exact same advanced computational technique that astrophysicists use to model the violent mergers of binary black holes and the high-speed collisions of neutron stars. the exact type of extreme cosmic events that the Laser Interferometer Gravitational Wave Observatory, or LIGO, routinely detects. When the research team programmed the exact parameters of a collapsing warp bubble into their advanced digital simulation models, the supercomputers churned through the complex tensor mathematics and produced a highly detailed, visually stunning rendering of a space-time catastrophe. The digital data revealed that the sudden disintegration of an artificial warp field creates a massive, high-frequency burst of gravitational waves that propagates outward into the universe at the absolute speed of light. These are not ordinary slow-rolling ripples in space-time, like the ones generated by massive astronomical events out in deep space. When two colossal black holes orbit and eventually smash into each other millions of light years away from Earth, they produce long, low-frequency gravitational waves that require incredibly large multi-kilometre laser interferometers to detect. A collapsing warp drive bubble, by absolute contrast, is a highly compact, artificially concentrated structure, which means its sudden, violent destruction produces an incredibly sharp, high-frequency signature that looks completely unique compared to any known natural astrophysical phenomenon in the catalogue of science. The digital simulations demonstrated that as the warp bubble wall undergoes its rapid structural failure, the positive mass and internal energy fields composing the drive shell begin to violently oscillate and shear against the surrounding cosmos. These intense, high-speed vibrations act like an incredibly powerful cosmic drumstick, violently striking the drumhead of space-time, sending out a distinct, highly structured series of gravitational wave packets. The simulated waveform possesses a very specific geometric profile. It begins with a sudden, massive spike in amplitude as the initial structural integrity of the bubble wall snaps, followed immediately by a rapid, high-frequency ringing phase where the leftover gravitational energy echoes and dissipates back into the flat, baseline vacuum of the universe. This specific ringing pattern is universally known in numerical relativity as a ring-down signature, and its exact frequency, duration, and modulation are directly determined by the physical size of the spacecraft, the thickness of the drive shell, and the cruising velocity the vehicle was maintaining just before the malfunction occurred. But the most fascinating and entirely unexpected revelation to emerge from these supercomputer models was the physical behaviour of the passenger region located at the absolute centre of the collapsing bubble. For the entire duration of the stable interstellar voyage, this central interior pocket remains perfectly flat, calm, and completely isolated from the extreme gravitational forces ripping through the outer boundary walls. But the moment the active warp drive shell suffers its critical failure and begins to disintegrate, that protective flat haven is instantly compromised. As the outer walls collapse inward, they compress the central passenger region with an absolute, unimaginable force. The simulation showed that the interior space undergoes a violent, hyper-rapid contraction, instantly crushing the physical hull of the starship, its delicate instrumentation, and any human crew members aboard into an infinitely small point of density. The final end state of a collapsed warp drive bubble is a pristine, newly formed miniature black hole. This means that a warp drive failure is an absolute, non-survivable event for the space explorers inside. There is no emergency escape pod that can be launched, no backup structural generator that can save the hull, and no mechanical system that can override the collapse once the instability crosses a specific mathematical threshold. In a fraction of a millisecond, the entire starship and everything inside it is cleanly converted into a localized singularity, leaving behind absolutely no physical debris, no floating metallic wreckage, and no drifting components. The only physical evidence that the starship ever existed at all is the newly formed miniature black hole drifting quietly through the cosmic void, alongside that sharp, high-frequency burst of gravitational waves racing outward into the universe to announce the exact location of the interstellar disaster to anyone who possesses the technology to listen. This profound insight has completely revitalized and reframed the entire field of SETI, which stands for the search for extraterrestrial intelligence. For more than 6 decades, traditional SETI initiatives have focused almost exclusively on scanning the night sky for artificial electromagnetic signals, using massive ground-based radio telescopes to listen for faint, patterned radio broadcasts, or searching with optical sensors for deliberate laser flashes coming from distant star systems. While this classic approach has been deeply inspiring and has successfully scanned thousands of stars, it has famously yielded nothing but an absolute deafening silence, a scientific mystery universally known as the Fermi paradox. If the universe is incredibly old and packed with billions of potentially habitable planets, why haven't we detected any radio transmissions from advanced alien civilizations? Modern warp drive physicists suggest a compelling answer to this paradox. Highly advanced spacefaring civilizations might have completely abandoned primitive radio communication technologies thousands of years ago, choosing instead to navigate the cosmos using sophisticated gravitational technologies that leave behind an entirely different kind of footprint. If an advanced extraterrestrial species has successfully mastered the extreme structural engineering required to construct and fly positive energy subluminal warp drives, or if they have discovered a viable loophole to operate classic faster-than-light metrics, they wouldn't be leaving behind a trail of leaking radio waves for us to detect. Instead, their interstellar commerce, their exploratory fleets, and the occasional catastrophic failures of their starships would be filling the cosmic vacuum with distinct high-frequency gravitational shockwaves. The sudden stops, starts, shifts in velocity, and catastrophic collapses of their interstellar vehicles would make the fabric of our galaxy actively buzz with a continuous murmur of artificial ripples. This means that humanity might already possess the initial tools to detect the presence of alien traffic across the Milky Way, provided we learn how to look for the right signatures. Our current generation of ground-based gravitational wave observatories, most notably the Laser Interferometer Gravitational Wave Observatory in the United States and the Virgo detector in Europe, were specifically engineered to listen for the massive, low-frequency cosmic groans produced by natural events like colliding black holes or merging neutron stars. Because of this specialised design, their multi-kilometre vacuum tunnels are largely insensitive to the incredibly sharp, high-frequency chirps that a collapsing alien warp drive would produce. But the global scientific community is currently planning and constructing a new generation of sophisticated, space-based observatories that could completely shatter these observational limitations. Foremost among these future projects is the Laser Interferometer Space Antenna, or LISA, an ambitious international mission led by the European Space Agency in close collaboration with NASA. Scheduled to launch into a massive orbit around our central sun, LISA will consist of 3 independent, highly sophisticated spacecraft flying in a perfectly precise equilateral triangle configuration, separated from one another by an immense distance of 2.5 million kilometres. Each individual spacecraft will house a pristine, freely floating gold-platinum cube that acts as a test mass, and the 3 vehicles will continuously bounce highly stable laser beams across the millions of kilometres of empty space, separating them to measure the absolute distances between those test masses with a precision that is smaller than the diameter of a single atom. Because LISA will operate in the quiet, undisturbed environment of deep space, completely free from the seismic vibrations, atmospheric disruptions, and thermal noise that plague ground-based detectors, it will possess a vastly wider observational window, allowing it to scan frequencies that are entirely invisible to Earthbound instruments. When LISA becomes fully operational, it will possess the theoretical capability to scan the entire fabric of our local galactic neighbourhood for the ultra-precise, high-frequency signatures mapped out by Katie Clough and her research team. If an alien exploration vessel suffers a catastrophic warp field failure anywhere within the Milky Way galaxy, or if a highly advanced species actively initializes a massive space-warping propulsion system near a neighbouring star system, the resulting ripples in space-time will sweep cleanly through the LISA triangle. The laser beams bouncing between the three spacecraft will register a highly specific, patterned shift in their interference profiles, mapping out the precise waveform of the event. Astronomers sitting at their computers on Earth would be able to read that incoming data and instantly distinguish it from any natural astrophysical event, recognizing the unmistakable signature of an artificial metric collapse. We could turn on our space-based detectors one day and discover that the galaxy is not an empty, silent desert, but a vibrant, active highway, providing absolute, definitive proof that warp drive technology is not only physically possible, but is actively being utilized by intelligent civilizations to conquer the vast voids of the cosmos. This profound realization shifts the entire narrative of space travel away from distant science fiction fantasies and firmly into the realm of modern, incremental scientific progress. It forces us to take a long, honest look at the current trajectory of human technology and ask a fundamental question. What will it actually take for our species to transition from writing mathematical equations on whiteboards to building a functional physical prototype of a warp-capable vehicle? The honest answer from the global physics community is a sobering dose of reality, mixed with a massive amount of long-term inspiration. The mathematics of the problem, particularly after the landmark breakthroughs of the 2021 Bobrick-Martyr framework and the 2024 Fuchs positive energy solution, has officially declared that the universe does not forbid warp travel. The laws of nature are fully cooperative, but the structural engineering required to realise those mathematical solutions remains completely light years beyond our current global industrial capacity. To build even a modest subluminal warp drive based on the most optimised modern designs, humanity would need to master the manipulation of matter at scales and densities that approach the absolute limits of physical reality. As we have seen, replacing the requirement for non-existent exotic matter means we must construct a drive shell out of ordinary positive energy matter that has been compressed to densities matching those found inside the dead cores of collapsed white dwarf stars or hyperdense neutron stars. A single teaspoon of material at those extreme densities would weigh several billion tons on the surface of the Earth. If you were to drop a small brick of this material onto the ground, it would instantly slice through the crust of our planet like a hot knife through butter, sinking rapidly toward the central core due to its immense, concentrated gravitational pull. Humanity currently possesses absolutely no industrial mechanism to harvest, compress, shape, or stabilize matter at these neutron-degenerate levels. At these extreme densities, the standard electronic bonds that hold ordinary atoms together are completely smashed apart by the immense pressure, forcing electrons to separate from their atomic nuclei and creating a highly volatile, ultra-dense plasma that wants to violently expand and explode if the external pressure is ever removed. To shape this material into a sleek, functional starship hull that can wrap around a human habitat without instantly collapsing under its own massive gravity or exploding outward into space, we would need to develop an entirely new field of engineering, gravitational material science. We would need to learn how to generate and control artificial magnetic fields and localized gravitational constraints that are millions of times more powerful than anything we have ever produced in our most advanced magnetic confinement fusion reactors. This scale of industrial manufacturing would require us to completely abandon our traditional earthbound factory systems and transition into a true spacefaring civilization that can manipulate the resources of entire celestial bodies. We would need to establish automated robotic mining colonies across the asteroid belt to harvest millions of tons of heavy metals, transport those materials to massive manufacturing stations orbiting deep in space, and utilize the immense gravitational well of objects like Jupiter or the raw energy output of massive solar collector arrays to compress those materials into the necessary hyper-dense drive shells. It is a multi-generational project that will require centuries of continuous technological innovation, a stable global economy, and a shared planetary commitment to long-term scientific discovery that transcends standard political, national or financial cycles. But while the physical construction of a full-scale interstellar warp ship remains a distant milestone on our civilizational horizon, the journey towards that destination has already begun to yield profound, real-world scientific rewards right now. The intense, highly focused academic research into warp metrics is forcing theoretical physicists to confront the absolute boundaries of our current understanding of reality, driving them to chip away at the single greatest unresolved mystery in modern science: the unification of general relativity and quantum mechanics. General relativity, Einstein's masterpiece, perfectly describes the universe on a grand scale, explaining how massive stars, sprawling galaxies, and the cosmos as a whole behave through the continuous smooth bending of spacetime. Quantum mechanics, by absolute contrast, perfectly describes the universe on a microscopic scale, detailing the chaotic, probabilistic behavior of subatomic particles, electromagnetic forces, and quantum energy fields operating within flat space. Both of these theories are phenomenally successful, verified to an extraordinary degree of precision by a century of independent laboratory experiments and astronomical observations. Yet, when physicists attempt to combine the mathematical equations of general relativity with the equations of quantum mechanics to analyze environments where extreme gravity and subatomic phenomena overlap, the math completely breaks down, yielding nonsensical answers like infinite energy densities or absolute mathematical impossibilities. The universe cannot operate on two completely separate, incompatible sets of blueprints. There must exist a deeper, more fundamental framework that seamlessly unifies these two descriptions of reality, a single overarching theory universally known as quantum gravity. Warp drive configurations sit precisely at the absolute intersection where these two incompatible theories are forced to collide. To understand how a warp bubble wall stabilizes, how the quantum vacuum fields inside a Casimir cavity react to intense space-time curvature, or how Hawking radiation behaves along a rapidly moving superluminal boundary, you cannot rely on general relativity or quantum mechanics in isolation. You are forced to utilize tools from both fields simultaneously, driving theoretical physicists to pioneer new mathematical techniques and develop preliminary frameworks for quantum gravity, such as string theory, loop quantum gravity, and semi-classical relativity, every single equation written to optimize a warp drive metric, every single supercomputer simulation run inside tools like Warp Factory, and every single laboratory experiment designed to measure subtle quantum vacuum shifts acts as a powerful crowbar, slowly prying open the lid of this cosmic mystery. the pursuit of the stars is actively teaching us how the absolute fabric of reality holds itself together at the most fundamental level. The continuous search for a unified description of reality highlights a profound truth about the nature of human innovation. The pursuit of an incredibly ambitious, seemingly impossible objective often acts as the primary catalyst for our most significant near-term scientific discoveries. Even if humanity fails to light up a full-scale physical warp drive for centuries, the rigorous mathematical framework we are developing to understand space-time manipulation is already transforming our approach to modern physics. It forces our brilliant theoreticians to routinely operate at the absolute limits of established physical laws, testing the boundaries of what nature allows, and discovering hidden loopholes that standard classical engineering could never uncover. By systematically probing the intersection of general relativity and quantum mechanics through the specialized lens of warp metrics, we are forcing these two incompatible descriptions of our universe to interface with one another in highly controlled, structured mathematical environments. This process is providing invaluable clues that will eventually guide us toward a complete theory of quantum gravity, unlocking the deepest secrets of cosmic history, from the first fractions of a second during the Big Bang to the extreme physics occurring inside active black holes. Now let us examine the profound societal and psychological transformations that will occur as humanity continues down this theoretical and engineering path. The moment a civilization begins to transition from a planetary mindset to an interstellar perspective, its entire cultural foundation undergoes a massive, permanent shift. For our entire recorded history, human existence has been defined by a deep-seated sense of geographic limitation. Every war ever fought, every empire that ever rose and fell, and every economic system ever designed occurred on a single isolated world with strictly finite resources. We are accustomed to thinking in terms of scarcity, competition, and borders because our physical playground is inherently small and locked away by the immense desolation of the cosmic vacuum. But the moment the physics of warp drives changes from an abstract chalkboard concept into a plausible, multi-generational engineering roadmap, those traditional boundaries begin to dissolve. The realization that the starry night sky is not a collection of unreachable, beautiful islands, but a vast network of destinations that we can eventually learn to visit changes the very heartbeat of human ambition. This civilizational shift requires us to rethink our long-term survival strategy. As a species residing entirely on a single planet, humanity is incredibly vulnerable to an assortment of existential threats. A massive asteroid impact like the one that ended the reign of the dinosaurs, a sudden global supervolcano eruption, a self-inflicted nuclear or biological catastrophe, or the inevitable long-term swelling of our central sun could instantly wipe out our entire cultural and biological legacy in a historical heartbeat. Becoming a multi-planetary species by establishing small, fragile colonies on Mars or the Moon is an important initial step toward diversification. But true civilizational security can only be achieved when we break free from our home solar system entirely. An interstellar civilization, scattered across multiple independent star systems and utilizing the limitless energy and material resources of the wider galaxy, becomes virtually immune to absolute extinction. If a localized catastrophe decimates one stellar neighborhood, the human species continues to thrive, innovate, and preserve its accumulated knowledge in dozens of other systems across the cosmic void. To fully grasp how we might begin to execute this grand diversification strategy, we must turn our attention to the immediate milestones on our technological horizon. Long before we possess the industrial capability to build a hyper-dense, moon-sized positive energy drive shell capable of carrying human passengers, we will likely master the construction of microscale warp fields. In high-tech physics laboratories across the globe, experimentalists are already developing high-precision instrumentation that can measure the most subtle, microscopic distortions in the fabric of spacetime. By utilising advanced metamaterials, ultra-powerful laser arrays, and highly specialised quantum cavities, future researchers might succeed in creating a microscopic warp bubble that spans only a few nanometers in total width. While a subatomic warp bubble cannot carry physical cargo or human explorers, its successful generation would represent a monumental historical turning point. It would provide the absolute empirical validation that human technology can actively manipulate the metric of space in a controlled laboratory environment. Furthermore, these micro-scale warp fields could possess immediate, revolutionary applications for global technology. A microscopic warp bubble could be utilised to manipulate information rather than physical matter. By warping space-time at a subatomic scale inside advanced computer processors, engineers could theoretically construct communication channels where informational signals bypass standard electronic resistance, translating through the internal circuits at customised relativistic speeds. This would lay the foundation for a completely new paradigm of hyperfast computing, leaving our current generation of silicon-based chips and basic quantum processors completely obsolete. As these micro-scale technologies steadily mature over decades of continuous refinement, they will pave the way for the development of unmanned interstellar probes powered by scaled-down warp metrics. Imagine a compact, fully automated scientific vessel, roughly the size of a modern drone, equipped with a highly optimized subluminal warp shell. Because this automated vehicle carries no human crew, it requires no heavy life support systems, no massive water and food supplies, and no delicate radiation shielding against quantum horizon fluctuations. The passenger region at the centre can be exceptionally small, containing only a cluster of advanced solid-state sensors, high-resolution cameras, and an array of sophisticated deep space communication lasers. This massive reduction in total volume translates directly into a dramatic decrease in the total amount of mass required to construct the outer drive shell. Instead of needing to harvest and compress an entire moon's worth of material to achieve the necessary metric curvature, engineers could fuel the microprobe's warp field using an amount of hyperdense matter that can be realistically manufactured inside an orbital facility. An unmanned vehicle of this design could be launched toward our nearest neighbour, Proxima Centauri, within the next 2 centuries. Cruising through the cosmic void at a steady, controlled subluminal velocity of 90% of the speed of light, the automated probe would bridge the 25 trillion mile gulf in just under 5 years. Throughout the entire transit, the onboard computers would remain in constant causal contact with mission controllers back on Earth. Because a subluminal warp bubble never forms an absolute event horizon that cuts off informational signals, the probe could continuously stream real-time telemetry, mapping out the sparse interstellar medium, measuring the structural stability of its own warp field, and providing humanity with its very first direct, close-up look at the true environment of deep interstellar space. Upon approaching the destination star system, the automated probe would execute a carefully pre-programmed gradual deceleration sequence, systematically relaxing the space-time curvature of its drive shell to avoid generating a devastating, hyper-energetic particle blast that could damage the target system. Once the warp field is completely deactivated, the probe would coast into a stable orbit around Proxima Centauri b, the Earth-sized exoplanet orbiting within the star's habitable zone. The onboard cameras would capture breathtaking, ultra-high-resolution images of an alien world surface, analysing its atmosphere for definitive signs of biological activity, mapping its oceans and continents, and sending that historic planet-shaping data back to Earth via its high-powered laser communication array. The arrival of those signals would mark the official dawn of humanity's status as an active interstellar species, proving that our theoretical equations were fully capable of breaking our cosmic isolation. The success of these robotic scouting missions would provide the necessary engineering data, economic momentum, and civilizational confidence to begin planning the ultimate phase of our journey, human-crewed interstellar expeditions. The transition from automated probes to human habitats will represent the single greatest industrial challenge our species will ever confront, demanding an absolute mobilization of global resources and a level of international cooperation that completely transcends our current geopolitical landscape. To build a starship large enough to sustain a human crew for a multi-year voyage, we will be forced to establish a permanent, industrialized infrastructure entirely in space, operating completely independent of the Earth's surface. This orbital infrastructure will likely center around massive, automated manufacturing hubs positioned throughout the asteroid belt and orbiting the outer gas giants. These facilities will utilize advanced robotic swarms to systematically strip mine resource-rich asteroids, harvesting millions of tons of platinum group metals, silicates, and volatile gases. This raw material will be transported via automated cargo haulers to construction shipyards situated in stable orbits around the Moon or in deep interplanetary space, where immense solar-powered particle accelerators and magnetic compression rings will begin the arduous process of manufacturing the hyperdense degenerate matter required to form the Starship's warp shell. The shipyards themselves will be sprawling cities in space, housing thousands of specialized engineers, robotic technicians, and computer scientists working in a zero-gravity environment to assemble the complex interior habitats, advanced fusion power plants, and metric generator arrays. The design of the human habitat nested at the absolute center of the warp shell will be a marvel of structural engineering, because the passenger region remains a perfectly flat, calm pocket of Minkowski spacetime throughout the entire interstellar transit. The internal layout of the Starship does not need to look like a cramped utilitarian submarine. Architects can design expansive, comfortable living spaces that prioritize human psychological well-being during the years-long journey. The habitat can include massive, self-sustaining agricultural biomes that continuously recycle water, generate oxygen through specialized plant life, and produce fresh food for the crew. Centrifugal rings can be integrated into the habitat structure to spin smoothly, generating a comfortable level of artificial gravity via inertial force to prevent the crew's muscles and bones from degrading during the long voyage. The crew selected to command this historic voyage will represent the absolute pinnacle of human capability, consisting of highly trained physicists, engineers, astrobiologists, medical doctors, and pilot operators who have dedicated their entire lives to preparing for the mission. As they step aboard the completed vessel and secure themselves within the central passenger module, they will be fully aware that they are leaving behind everything and everyone they have ever known. Even though a subluminal warp drive travelling at 95% of light speed completely eliminates the severe time dilation effects of special relativity for the passengers inside, ensuring that their onboard clocks tick forward at the exact same rate as the clocks back on Earth. The immense physical distance of the journey still dictates a strict, unyielding timeline. A round-trip voyage to Proxima Centauri, including a brief exploration phase on the surface of an alien world, will require nearly a full decade of absolute terrestrial time. The children born on Earth the day the Starship lifts off, will be attending middle school by the time the crew finally returns home. When the Starship clears the orbit of the Moon and manoeuvres into its designated launch trajectory, the captain will engage the primary metric generator system. Inside the central habitat, the crew will hear absolutely nothing unusual. There will be no deafening roar of chemical rockets, no violent mechanical vibrations, and no crushing acceleration forces pressing them into their seats. They will remain fully capable of walking across the living modules, sipping a cup of coffee, or conducting scientific experiments in perfect comfort. But outside the Starship's thick hull plates, the universe will completely transform. The metric generator arrays will unleash an incredibly powerful, highly structured gravitational field that violently grabs the surrounding fabric of spacetime, compressing the universe directly in front of the vehicle and stretching it out behind. To an outside observer watching from an orbital observation station near Earth, the Starship will appear to instantly vanish into a spectacular distortion of light. As the warp bubble accelerates toward its subluminal cruising velocity, the extreme curvature of its boundary walls will act as an incredibly powerful gravitational lens, violently bending and distorting the light from distant background stars into a shimmering, fluid ring of cosmic energy that wraps completely around the vehicle. The Starship will literally surf out of our solar system on a newly engineered geometric wave, ploughing through the empty desolation of deep space at a velocity that leaves the fastest chemical rockets in history looking like completely stationary objects. The long dark night of human isolation will officially come to an end as our species begins its grand, slow expansion into the local stellar neighbourhood. As we look toward this inspiring, distant future, we must remain deeply grounded in the honest, step-by-step reality of scientific progress. The realization of warp travel is not a puzzle that will be solved by a single accidental breakthrough in a basement laboratory, nor is it a secret technology that a government agency is hiding away from the public. It is a monumental, centuries-long mountain that humanity must systematically climb, one individual equation at a time, one validated computer simulation at a time, and one delicate laboratory refinement at a time. The absolute value of modern warp drive research is that it has given us an ironclad mathematical compass, providing definitive proof that our ultimate cosmic ambitions are not blocked by the absolute laws of physics. The universe is not an inescapable prison. It is a grand, challenging wilderness that is patiently waiting for us to develop the maturity, the resources, and the wisdom to cross its borders. The work currently being executed by specialised international research collaboratives, independent physicists, and computer computational teams represents the foundational bedrock upon which this entire future will be constructed every time a scientist inputs a new design parameter into numerical relativity software like Warp Factory, discovers a clever geometric twist that lowers the matter density required for a positive energy shell, or successfully measures a subtle quantum vacuum fluctuation inside an advanced laboratory cavity. They are placing a vital brick into the highway that will eventually carry our descendants to the stars. It is an extraordinary privilege to live in an era where the boundary line between science fiction and rigorous theoretical physics is actively being redrawn before our very eyes, transforming the wildest dreams of our ancestors into an actionable mathematical roadmap for the future of humanity. The deep architectural work currently being mapped out by specialised international research collaboratives, independent physicists, and computer computational teams represents the foundational bedrock upon which this entire future will be constructed. Every single time a dedicated scientist inputs a new design parameter into numerical relativity software like Warp Factory, discovers a clever geometric twist that lowers the matter density required for a positive energy shell, or successfully measures a subtle quantum vacuum fluctuation inside an advanced laboratory cavity, they are placing a vital brick into the highway that will eventually carry our descendants to the stars. It is an extraordinary privilege to live in an era where the boundary line between science fiction and rigorous theoretical physics is actively being redrawn before our very eyes, transforming the wildest dreams of our ancestors into an actionable, mathematical roadmap for the future of humanity. This slow, systematic transformation of human capability leads us directly to the ultimate cosmic question that has haunted philosophers and scientists for centuries. What is our final destiny among the stars? When we look back at the grand timeline of human history, we see a species that has continuously refused to accept the limitations of its environment. When ancient humans stood on the shores of vast oceans, looking out at a horizon that appeared to be the absolute edge of the world, they did not simply turn around and stay inland. They chopped down trees, constructed fragile wooden boats, and sailed directly into the terrifying unknown, eventually populating every corner of our planet. When our 20th century ancestors looked up at the moon, a distant silver sphere suspended in the cold vacuum of space, they did not dismiss it as an unreachable celestial spirit. They built towering chemical rockets, strapped themselves into tiny metal capsules, and walked across its dusty surface, leaving behind footprints that will remain undisturbed for millions of years. Now, as we face the monumental 25 trillion mile gulf separating our solar system from Proxima Centauri, we are being called to execute that exact same exploratory instinct on a truly cosmic scale. The immense physical barriers that currently stand in our way, the staggering amounts of mass required to shape a positive energy drive shell, the extreme material densities that defy our current manufacturing capabilities, and the complex quantum physics that governs the boundaries of a warp bubble are not reasons to give up or retreat into a state of permanent civilizational stagnation. They are simply the initial structural parameters of a grand problem that we are fully capable of solving over generations of continuous innovation, learning, and disciplined exploration. The ultimate breakthrough will happen when our descendants finally bridge the gap between abstract mathematical equations and large-scale industrial execution. Imagine a historical moment several centuries into our future when a fully unified spacefaring human civilization successfully completes the construction of the very first operational crewed interstellar starship equipped with a physical warp drive. This magnificent vessel, assembled in the quiet gravity-free environments of an orbital shipyard, will stand as the absolute monument to human intelligence, combining our deepest understandings of general relativity, quantum mechanics, and cosmic engineering into a single, functional vehicle. As the ship's primary metric generator arrays light up for the very first time, a profound transformation will ripple across the cosmos. The vehicle will not blast through space by burning through mountains of chemical fuel or throwing radioactive exhaust out of a mechanical nozzle. Instead, it will gracefully manipulate the absolute geometry of the universe itself, compressing the fabric of space-time ahead of its path and stretching it out behind to glide effortlessly across the interstellar void. The deep-seated geographical isolation that has defined the human experience since the dawn of our species will instantly evaporate. The starry night sky will no longer look like a cold, beautiful collection of unreachable cosmic destinations. It will become our new backyard, a vast and inviting frontier, open for peaceful scientific discovery, colonization, and long-term civilizational growth. The human crew aboard that historic maiden voyage will cross the immense distance to Proxima Centauri, not in 70,000 years, but in a matter of a few short years of absolute terrestrial time. They will step out of their flat, calm passenger region to look up at the foreign sky of an alien world, realizing that they have successfully broken the cosmic chains that kept humanity bound to a single speck of dust. From that moment on, the slow expansion of our species will become completely unstoppable. We will systematically spread across the local stellar neighbourhood, establishing thriving, self-sustaining human communities around neighbouring stars like Sirius, Vega and Alpha Centauri, ensuring our permanent protection against any localised existential threats and securing our cultural legacy for millions of years to come. The mathematical blueprint has officially declared that this magnificent outcome is not forbidden by the absolute laws of nature. The unyielding equations of general relativity have revealed a hidden loophole in the structure of spacetime, proving that the ultimate cosmic speed limit is a doorway rather than a wall. The engineering required to cross that threshold is admittedly not close. It represents a towering mountain of industrial development, material science breakthroughs, and orbital infrastructure construction that will require centuries of patient, dedicated effort to conquer. The honest, realistic verdict of modern science is an absolute requirement for civilizational patience, combined with a continuous, unwavering commitment to keep working, keep learning, and keep exploring. We must approach this monumental journey exactly as we have approached every great scientific achievement in our history. One equation at a time, one computer simulation at a time, one validated laboratory experiment at a time, and one incremental geometric refinement at a time, because the absolute distance to Proxima Centauri is 25 trillion miles, and a highly resilient, intelligent species that successfully walked across the surface of the Moon, landed highly advanced robotic rovers on the rust-coloured plains of Mars, and engineered high-precision laser interferometers to detect the faint gravitational waves echoing from merging black holes, will eventually find a real way to cross that void, conquer the stars, and fulfill its final cosmic destiny as a true interstellar civilization.